Hi, this is section 4.4, second day, and we're dealing with the first fundamental theorem of calculus, which we did in the previous lesson, and today we're going to do the second fundamental theorem of calculus, as well as the mean value theorem for integrals, average value, and average value. Okay, so just a quick refresher, guidelines for using the fundamental theorem of calculus. Provided you can find an antiderivative of f, which is not always the case, you can't always do that, you now have a way to evaluate the definite integral without using the limit of a sum. Made things easier. Number two, when applying the fundamental theorem of calculus, review this notation. This is the lower limit. This is the upper limit of integration. This is your function multiplied by dx. dx is a shortcut way of delta x, since we're doing the infinite sums of adding up all this area under the curve. Capital F of x is the antiderivative of little f of x, and we do this right bracket and we evaluate from a to b again. Plug in b and subtract out what happens when you plug in a. And then here's an example. You do not need the constant of integration for a definite integral. Definite integral has the limits. Indefinite integral does not have the limits, because if you include the c's would just drop out anyways. So that's a quick review. Another thing that we're going to need today is the derivative using the chain rule. So let's do one example. If I have the derivative of the sine of x cubed. To do that, remember you take the derivative of the outside, derivative of the sine is cosine, leave the inside alone, and then what else do we need to do? Well, we need to chain off by the derivative of what's inside. So this would be times 3x squared. So this is my chain. We'll need that later on. So what are we doing today now? Well, this theorem, 4.10, says that we have a mean value theorem. If f is continuous on the closed interval a to b, then there must exist some number c in the closed interval a to b such that the integral is equal to this. Now what is this? Well, this is b minus a is a length, this is a height. So if I go to some integral, say for instance I have a curve like this, and I go from a to b. What happens is that what I want to do is take this area here, let's call this r, so that would be the area of that region, and I want to squish this down. So say for instance I extend these lines, and this r is a big thing of goo. What I want to do is I want to push this line down, just take a pen or I don't know, whatever, and then push this down so that we end up with a rectangle. So we want to transfer this over to this shape here. So this is a, this is b, and then somewhere in here I'm going to get a rectangle that has exactly the same area, which we can call r. Now in doing that, that would give us an equivalent line that would be somewhere, it's kind of the average of all these y values, would be across here. That dotted line is equivalent to this height over here. Now look at what this says. Well, it says that there is some c in this interval such that this dotted line would cross, I can find a c value here, and this would be f of c. Now in looking at this distance right here is b minus a. Oh, b minus a is this length, and then f of c is this right here. So this just says that this area with this curve would be equivalent to this area of this rectangle. That's all this is saying. Now we don't use this one too much in the form that it is, but what we do is that we look at something that's called the average value. So once again, I said that this dotted line across here kind of sums up, or is kind of the average of all these points. Well, how many points do I have from here to here? Well, there's an infinite number of points along this curve. If I took them all and added them all up and divided by how many I have, I'd be here for a really long time. So this is how they take this average value to be. The average value is just going to be the height, which is this f of c here. So in other words, to get this average value thing, all I need to do is get rid of this b minus a. And that's what we do down here. The average value is 1 divided by b minus a. And I can say that this is equal to f of c. F of c is equal to 1 over b minus a, and the integral from a to b of f of x dx. You do use the average value quite a bit. The mean value theorem, well, it's an existence theorem. And so an existence theorem just says that it guarantees some value of c here where it's going to cross this function. It might cross many times, but it's going to cross at least one time. So that's what we got. Now let's look at some examples and see what we're doing here. Average value of this, so average value, this is my a, this is my b, so all I do is 1 over 3 minus 1 times the integral of x cubed dx. That would give me my average value. So it's going to be, I got to put the limits in here, 1/2 times, what's the antiderivative of x cubed? Well, it'd be x to the 4th over 4. And I'm going to evaluate that 1 to 3. So you can pause this and try this, but I've already started. Take the 1/2, plug in the 3 first. 3 to the 4th is 81, so I get this. Minus the 1/2, plug in the 1. 1 over 4. Yeah? And so then you can simplify this and you get a value of, and to simplify this I get 10. Now if you want to check this with your calculator, remember that you can do the integrals on your calculator. You should do these out by hand, but you can always use your calculator as a check. But if I use this one here, what I can do is I just go second calc, and then I have the antiderivative there, and I'm going from 1 to 3, and I should get 20. Yep. And then I still have to take the 1/2 because that's the averaging portion of it, divided by the length of the rectangle. Okay? So that would be the average value of a function. Now moving on, if we find the average velocity, why don't you go ahead and do this one. Average velocity means that we would take 1 over b minus a. Since I give you the velocity, I'm asking for velocity, then you have to integrate and then divide back. And so this is from pi over 4 to 3 pi over 4. Go ahead and do this, pause, and then I'll just have the result up here and then talk about it a little bit more. So 1 over b minus a is 1 over pi over 2 when you take the subtraction of those two. And then the reciprocal would give me 2 over pi. Antiderivative of sine of t is negative cosine of t. Plug in 3 pi over 4, I get negative square root of 2 over 2. That makes it positive. So I get 2 positives after plugging those two in. And then this is just half of these plus half of these makes a whole one of those. So this is just 2 over pi. And inside the bracket, I just get 1 square root of 2. All right? So that's just 2 square root of 2 all over pi. That would be my average velocity on this interval of my function. Okay, now if I move on a little bit, let's look at a relationship here. We've done average velocity before when given a position function. Well, when this happens, the average velocity is found when we have the position function and we go ahead and find the slope of the secant on this interval. So go ahead and do this and let's compare and see what happens. So when I figure all this out, I find the position at 3 pi over 4 and pi over 4, figure out those two values. These are my y coordinates, so to speak, and then these would be the x coordinates. And so I do the change in the y's over change in x's, which is actually change in x over change in t, but that's okay. And so I take this difference and look at what I end up with. Wow, this is exactly what I had up here. So finding the average value is the same. And you can think about it like this. Average velocity. If I ask you to find the average velocity, think, oh, I got to take the slope of the secant of the position function. I don't have the position function. How do you get it? Well, you take the antiderivative. So you can use this if you're given the velocity and finding the average velocity. If I ask you to find the average velocity and I give you the position function, you find the slope of that one directly. And you don't even directly need the calculus. Okay, so these two are very much related. Now if you notice, this one I did put in some plus c. Well, look what happens with that plus c. It just cancels off anyways. So it didn't matter if this was 2 or 57. I'd still end up with this value right here being my average rate of change, or average velocity in this specific case. Okay, next one is that we want to find the value c that satisfies the mean value theorem for integrals for this one right here. Okay, so if you remember from up above, let me pause this and get, so I want to find the value c that works for this, and so what I'm going to do then is try to set it up with this theorem right here. So I have the integral from a to b, well that's 1 to 3 of 9, I'm going to write this as 9x to the negative 3 dx. Okay, so that piece is equal to f of c, I don't know what c is going to be, and then b minus a, which would be my 3 minus 1. Okay, now what I want to do is find this value of c. So I take my antiderivative here, this would be to the 1 higher power, so it would be x to the negative 2 divided by negative 2, evaluated by from 1 to 3, and that's going to be equal to f of c times this. So I want to solve for f of c, so really I'm finding the average value anyways, which is my f of c. Now if I go ahead and evaluate this numerator right here, I'm going to get 4. I'm going to let you go ahead and do that and try that. And then I still have this 2, so f of c is going to be equal to 2. Now that's not my final answer. What they're saying for us is that we want to find out what c is. Well, here's my function f of x. If the y value is 2, how am I going to find out what f of c is? Well, I set them equal to each other, so I go 2 is equal to 9 over x cubed. And so if I solve this one out, I get x cubed is equal to 9 over 2, and x is equal to cube root of 9/2, which is approximately 1.6509. And when I say x here, this should actually be c. That's my c value right there. Now graphically, what does this mean? So I'm going to graph this 9 over x cubed, and then I'm going to integrate and find the area. So 1, 2, 3. And when I do that, that gives me the area of 4, which is what we found in our problem over here. Now what I'm going to do is, though, I need to divide that by 2 because that would be the length of my interval. And so what I'm trying to do is find out what height would give me my average. It's not 4 up here, but it's going to be 2 down here because I divide it by 2. So if I go y equals 2 for my other value, shoots across, this rectangle, if you can picture this right here, would be the equivalent area to all this darkened shade here. And so if I just find that value by doing the intersect, number 5, and then I get that same value that I'm looking for over here. So that's kind of the concept that we're dealing with. This c value would be the x value. Now moving on to the second page, second Fundamental Theorem of Calculus. With this, what we've had so far is a definite integral, and we have 2 constants, and then we can go ahead and find that area under the curve. What happens though is that sometimes we want the integral to be a function of x, and so this upper limit would be a function of x. In this case it just says x, but later on we'll get into some different functions to be there. And this f, not to confuse things, f has to be a different variable than this one here. So I need f of t dt, where this would be an x. Now what the second fundamental theorem of calculus says is that really if you take the derivative, if you take the antiderivative and then take the derivative again, you're going to end up with our same function back. So what I want to do is give you some problems here to try. I'm going to do the first one with you, and then you're going to try 1 through 4. So, and I'll come back to explain this one later, or I'll explain in class. So if I have this one, what this says is that I want to find g prime, given this integral. This upper limit is x. Let me show you how this is done. So if I want to find out what g of x is, I just take this integral and evaluate it. So what's the antiderivative of the sine, which would be negative cosine, and it is of t. and I'm going to evaluate this from 0 to x now. And so g of x, notice that this does say g of x, and so I'm going to end up with a function of x. So I take the x and plug it in. Don't forget to subtract and plug in the lower limit. A lot of times people forget to do that with the 0, but the 0 sometimes yields a number that's different than 0. And in fact, in this case, this would be a 1. So I'm going to get g of x is equal to negative cosine of x plus 1. Now what the instructions say, though, is find g prime. I kind of ran out of room here, so to find g prime, I take the derivative of this. Well, the derivative of the cosine is negative sine. With the negative there, I get the sine. So this would be the sine of x. What's the derivative of a constant? Derivative of a constant just goes away. So g prime is equal to sine of x. So now look at some patterns and see if you can figure this out. I want you to do 1 through 4 and see what you find out for g prime of x. Pause this and go ahead and do that. So now looking at this, I hope you did pause this and go ahead and try to do these the long way. Maybe after this one you stop doing it the long way, though, because you figured out the pattern. And I hope you did. What happens then is that whenever we look at this and take the derivative after we've taken the antiderivative, this constant, whatever we plug in there, will go away, because when I take the derivative of the constant, it disappears. So really all you're doing is you're taking this x and you're going to plug it into the function. That's all how you do this. And this is the second fundamental theorem of calculus. We're taking the derivative of the integral evaluated from a constant to a variable of some function. Take the x, plug it in. Boom, done. Wow, it's so easy. It does get more difficult, but let's see how this goes. If I do g prime of x here, what do you think? Well, just take the x, plug it in, and I'm going to get x. Done. Now, if you want to go ahead and do this the long way again, go ahead, please. Find the antiderivative of this, plug in these values, and then take the derivative again. You're going to get back to here. Now, here's an interesting example, because I alluded to this at the very beginning of this lesson. There's going to be some antiderivatives that we can't find. This is one of those cases. I don't know the antiderivative for this offhand. You can maybe find it on, what's that guy's name? Wolfram. But if I do want to find g prime, I can do that, though. I can circumvent all this by taking the derivative, take the x, put it right in there, and so g prime of x is going to be 1 plus x cubed. Done. Isn't that easy? Students really struggle with this, though. So the sooner you can understand this, the better off you are. Need to ask questions in class, please go ahead and do so you do understand this. Okay? Now, we need to go back and do this the long way, because now we have a function that's different than just plain x. So let's go ahead and try to do this one. So if I evaluate this one, remember that the antiderivative is negative cosine of t, and I'm evaluating from 0 to x squared. So g of x is equal to negative cosine x squared plus my 1 again. If I take the derivative, g prime of x, what happens now? Oh, wait a second. I am going to get the sine of x squared, but what else do we need to do? Well, I need to chain by this. So this is the only little nuance that we have to additionally put in. The constant will go away again. So I go g prime, yeah, I plug this in, but I also need to chain, because my function is different. My function in my limit is different than just a plain x. So what are we chaining off? Well, this is the thing that we chain off, the upper limit, whatever function that is. So if I go ahead and do this one, let's do the shortcut way. Oh, I have to, because I don't know the function here, or the antiderivative. So this would be 1 plus, take your function, plug it in, this would be the sine of x cubed. But what else do we need to do? Do I need to chain off by the sine of x cubed? Or do I just need to chain off by the sine of x? Well, the chain rule is a composition of functions, so what function did I plug inside? Well, it's the sine of x. So that's the thing that I'm going to be chaining off. So this would be times negative cosine of x. We can clean this up a little bit. There you go. Now, what happens if this thing's in the lower limit? Well, if we did this the long way, we would have the 0 plugged in first and then the x squared plugged in second. Since it's plugged in second, we'd be subtracting. So what's that going to do? Well, g prime of x is going to be equal to, anybody know? Negative. Since this is the lower limit, it's going to be negative. Plug this x squared in. I'm not making the noise anymore. And then I get x to the 6th power. Don't forget your chain. Oh, is the chain going to be the derivative of x to the 6th or x squared? I'm pretty sure it's going to be the derivative of x squared because that's the function that we plugged inside, and that's what the chain rule does. Simplify that by putting the 2x out in front. G prime on this next one. Oh, look at both of those. Oh. Let's plug it in. 1 plus. We know that that's the sine of cube t. Oh, this is what we had here, right? So don't forget to chain off. What am I chaining off? Negative cosine of x. This is the lower limit, so I'm going to subtract by plugging in the x squared. So this would be 1 plus x to the 6th. Don't forget to chain off. It's the derivative of this thing here, so that would be times 2x. Put the 2x out in front again, put the negative cosine out in front, and you've got it simplified. And this leads us to the second fundamental theorem of calculus. So if I have the integral, they're kind of inverse functions of each other, but if I take the derivative of the integral, I'm going to be back at my function right here. And so that's what happens. If the function is in the numerator, and this is g of x, not just x now, you're going to have to chain off by the derivative of this top function. If the function is in the denominator, it's the lower limit, so I'm going to have to subtract off what we do. So we just plug in h of x into the f function and then chain off by the h of x. If I have both top and lower, then I do both of them. Plug in the top, plug in the bottom. There's the difference there. All right, this was a little long. I apologize, but welcome back. And we're starting the new semester with the second fundamental theorem of calculus. And this is a great little review of a lot of different things that we've done already this year. Thanks.